Generative Adversarial Network GAN has many variants, especially there are many different objective functions for training the discriminator and generator. The first GAN, introduced by Yang Fellow, he used this objective function, log 1 minus d gz. When you make new image from generator plus expectation of x p data, which means when you randomly sample a new real image from your training data point. So since the output of discriminator is in between 0 and 1, the discriminator try to maximize this objective function by reducing the output of d for the output of your generator. So when you generate a new image by using the generator model, the discriminator, the main objective of discriminator is we want to make the output of discriminator close to 0 when the input comes from generator. And also if the input of the discriminator is real image, comes from real data set, then we want to make the discriminator value close to 1. So in this case, usually your training data point located here, real data, and randomly generated data point in this, we want to make a d so that the d value here is 1. This is also 1. So the d value is very high in this area. So push it up for this training data point, but push down for this area. So that this area we have almost 0 discriminator value. And from this function training, maybe your discriminator function have very nice knowledge on where is the real data space and where is the empty space, where is never happen for real data. Okay. And from the discriminator, then we can train the generator so that we can minimize this objective function, total objective function. And since this is independent to your generator, so the generator only try to minimize this part. So the generator try to make the output of G so that the output of G make the discriminator having value 1, close to 1. So generator try to update the parameter so that your output value becomes more close to here, because when you train discriminator, this area is very high, the area very close to 0, and since the neural network always continuous function, we can easily think there is some uphill, right? And which means there is a gradient direction of this is here. So you can easily understand to increase the discriminator output, you have to follow this direction. So you have to follow this direction. So you can update your generator parameters so that the next iteration in the next round, you can generate more realistic image. Okay, so it makes sense, and it works very well. So the first GAN paper generated very surprising result. So after that, many people turn to GAN instead of variation autoencoder, and they make a very nice result afterward. Okay, but the log, sometimes log is too, steep. I mean, when you take the gradient of log function, this is, so for instance, when you have log x function, the gradient is 1 over x. This is fine when x is in between 1 and 2, then always the gradient value have some similar range. 1/2 to 1 will be the gradient value range when x is in between 1 and 2. But in this case, the x range is 0 to 1. In that case, the gradient range is 1 to infinity. So this is not good. No, this is not good. When your gradient has very high variance, it is very, very difficult to train. Very unstable case. Okay. So because of that, I think because of that, many people tune the objective function using some different form. Okay. So another very famous approach is WGAN. WGAN basically make this objective function so this is generator. Okay. Using a function f and just plus and minus. If the data comes from real data, then we take the plus function f. If the data comes from the generator, then we take the minus f. And we try to maximize this total objective function by controlling function f. And of course, function f can be defined with parameter because f usually defined with a neural network. Okay. And then we want to minimize this total function by controlling g, so that so usually the function f has high value if the input comes from real data, and the function has very low value if the x comes from the generator. And then the generator tried to fake the discriminator function f. So they want to make the corresponding output of the function f to be high, even if the input comes from the generator. Okay, and in the previous slide, I explained the log objective function was not good in a sense that the gradient can be very deep in some range and gradient can be very flat in some range, and such high variance on your gradient can cause some very unstable training property for your generator and discriminator, which can generate many difficulties when you train your neural network. So to resolve such problem, for remedy for that, the WGAN introduced some smoothness for the function. Okay, smoothness function. So here we have function f and f here. If the function f is very smooth, so if f prime or gradient f is very smooth, then maybe we can more stably train the generator and discriminator function f. So usually WGAN make the additional constraint f have to belong to one ellipsis continuous. Of course, this is very difficult, hard constraint. So we relax this constraint by using some clipping method. So details you can check the WGAN paper. But the main concept is we try to make function f very smooth, which means fx minus fy over x minus y distance absolute value less than or equal to 1. So which means the derivative of your function f or gradient of your function f always bounded by some constant. Okay, why this is great? In the previous example, so this is the real line. So every time when you pick a real data, it comes from this line, and every time you take the random generator value, then it took some value here. This f function, because this is very smooth, the function will have very high value here. So very high value. So when you take the function for this vertical line, so when you take the function value for this vertical line, the function value f will be very high here and very smoothly down as it moves away from the true point. Because we have to build a one ellipsis continuous function f, the output of function f will be very smooth. So this smooth function make a very stable gradient direction map like here, like this. Very smooth gradient direction map. So which make your training very stable. Whatever your initial generator generate some image, fake image, this WGAN architecture can give you very nice direction to train your generator and discriminator. Okay, that's the beauty of WGAN. Right. So when you read WGAN paper and original GAN paper by Yang Fellow, they explain the difference between WGAN and GAN using Wasserstein distance, W distance, and Jensen-Shannon divergence. This is also true, so there is clearly difference between W distance and Jensen-Shannon divergence, and WGAN used this W distance and GAN used this Jensen-Shannon divergence. But actually, I think the main difference between WGAN and GAN comes from this continuous property of f. So the continuous, very smooth property of f in WGAN can make very smooth gradient vector field compared to this log objective function for the original GAN, which make your training process become very stable. Why? So actually to make a W distance, you have to train the discriminator a lot of time using a lot of iteration. You need a lot of iteration to train your discriminator to convert your actual network really have W distance concept, and GAN network really have Jensen-Shannon divergence concept. So when you read the original paper, so this is some very complicated story, and I think this is unnecessary complicated story to understand the concept of GAN and W GAN. When you train infinite number of iterations using very tiny step size, eventually the discriminator converts to some very nice neural network parameters so that the output of your W GAN will give you W distance, what sustained distance between the true data space and your generation model by the generator. And original GAN will give you Jensen-Shannon divergence between the true data distribution and the generator distribution. But in reality, we don't really do some infinite number of iterations for training discriminator. We actually just this process, one iteration for updating discriminator, and then one iteration for updating generator, and then one iteration for updating discriminator, and so on. So we actually do not fully converge the discriminator. So we actually do not go to W distance and Jensen-Shannon divergence point. So yeah, this is quite good explanation. Mathematically understand the concept of W GAN and GAN. But in practice, I think the most important difference between W GAN and GAN is the gradient vector field between the W GAN and GAN. W GAN can make more smooth structure, so we can expect more stable training process.